In this video, you and I get to formally implement something called FlexVPN quote-unquote client that gives us the ability to set up multiple head-end peers that we could possibly connect to for fault tolerance purposes. And secondly, it also gives us an opportunity for the EasyVPN client, the spoke, and the EasyVPN server, the hub, to exchange network routing information without having to use a dynamic routing protocol. With that said, let's begin. The starting point for you and I in this video regarding the configuration of our hub and spoke topology is the functional working network that we left in our previous video. Now, in the previous video, we added AAA authorization to the hub, and we pushed some configuration over to the spoke. Specifically, we pushed out the information regarding the IP address that R2, R3, and R4 should use on their tunnel 0 interfaces. In this video, we're going to take that existing topology and we're going to go ahead and take a look at configuring R2, R3, and R4 as full-blown FlexVPN clients. Now you might ask, okay Keith, what's the benefit of having a FlexVPN client as opposed to just doing a tunnel interface that statically points to R1? And the reality is we're very likely going to have multiple hubs. And maybe this is on the West Coast, and maybe we have a couple of hubs over on the East Coast. And what if we want R2 to try this group of hubs, primarily if they're not reachable for some reason, there's a disaster, or they go out of service, to go ahead and try the second set? With a static tunnel, saying go to 15001, it's not very flexible. It takes the whole flex out of FlexVPN. Instead of pointing to one specific IP address as the far end of the tunnel, we can go ahead and tell this tunnel interface that we want the tunnel destination to be dynamic instead of being a fixed IP address. And then secondly, we can create this FlexVPN client configuration that can specify peers. So maybe we have peer 1, peer 2, peer 3 with their various IP addresses. So if peer 1 goes down, it's not reachable, the client will say, you know what, I'll go for peer 2. And if peer 2 is not reachable, it can go for peer 3. And it can continue trying for as many peers as we define as part of the client FlexVPN. Now, to make this all work, on the spokes, we are going to go ahead and turn on AAA new model, and we are going to create a network authorization list, just like we did on the hub, that effectively is going to tell these routers, hey, listen, if I have authenticated the peer with digital certificates, I'm considering that peer authorized, and I want to go ahead and use the authorization policy specified. So that authorization policy is going to be added to our existing IKE v2 profile. Now you might say, Keith, well, what's the advantage of linking an authorization policy to an IKE v2 profile? And the benefit of that is that inside of our IKE v2 authorization policy that we're putting into our IKE v2 profile, we can use the command route set, and we can call on an access control list that identifies, for example, 2 or 3 networks. So if R2 has the 10.2.2 subnet and the 10.22.22 subnet and the 10.222.222 subnet and so forth, we can identify all of those inside of an access control list, and then in our authorization policy, we can say, okay, regarding these routes, I want you to go ahead and push these routes up to the FlexVPN server so he knows about them. So it's a way to communicate routes between peers without even having to use a routing protocol. And that's how these pieces interact with each other. Now the great news is this, because we have 3 spokes to configure, we're going to do all 3 together. And that way, you and I will have 3 opportunities to revisit the commands used to implement this and reinforce the concepts of what goes in the authorization policy and how do we link it into our IKE v2 profile. On this spoke, we're also going to be using AAA. So to enable that, we're going to go into configuration mode and specify AAA new dash model, and we're going to create a method list for network authorization. We're going to call it author-list, and if this method list is called upon by R2, it knows it should use itself, the local router, as opposed to reaching out and going off to a AAA server group using Radius. Now on this FlexVPN client R2, if we want to push up various networks that are reachable via this FlexVPN client, we can do so. And to identify those networks locally on the router, we're going to create an access list. So on R2, we'll create an access list called route-acl, and we'll identify the 10.22.22 network and the 10.2.2 network. And you could have as many networks as we want in this list. And what's going to happen is when this FlexVPN client connects up to the FlexVPN server, in the authorization policy on this client, we can tell it to go ahead and advertise these specific networks up to the hub. And we'll do that here in just a few moments when we modify the authorization policy on this client. Now currently on this client, we're using tunnel interface 0 for our connectivity from this spoke up to the hub. And regarding this tunnel destination, the IP address is pointing to the other end of the tunnel is 15001. Now, you and I both know and love that as Mr. R1. That's his internet-facing IP address. However, what happens if R2 is reaching out and trying to connect to 15.0.0.1 and it's not reachable? Maybe R1 is down. Then what's R2 going to do? Well, in a fault-tolerant environment, we may have R1A and R1B, two separate routers. And maybe that second router at the hub site has an IP address of 15.0.0.2. Well, using the FlexVPN client, instead of actually hard-coding the actual IP address of a single device, we can tell this tunnel interface that we want tunnel destination to be dynamic. And because R2 is going to act as a FlexVPN client, we're going to configure the details of that client, including who our peers are going to be. So, for example, we can have peer 1 and peer 2 and peer 3. So maybe peer 1 can be 15.0.0.1, and peer 2 can be 15.0.0.2, and maybe peer 3 is 75.9.2.4 on the other side of the country or the other side of the world for the benefit of fault tolerance. So when the client kicks off its VPN tunnel, if it can't reach the first device on this list, it can then go to the second one and then the third one. And that's how using a FlexVPN client can build in that redundancy for the VPN. So again, the changes we're going to make here is we're going to make this tunnel interface, tunnel destination, and the keyword dynamic. We're also going to create a FlexVPN client configuration, which has the peer address of R1. So let's make the change on the tunnel interface. We'll go into tunnel interface configuration mode and simply say tunnel destination dynamic. And that will overwrite the previous tunnel destination 15001. Now, because we removed the 15001 aspect and we haven't yet created the client configuration for FlexVPN, the tunnel interface on R2 is pretty much worthless until we use that client configuration and point to the peer at 15001. Next, let's take this access list that we created, which was called route-ACL, which points to two networks, the 10.22.22 and the 10.22, and let's include that as part of R2's authorization policy. And specifically, that's the IKE v2 authorization policy. So once the access list is made part of that authorization policy, we'll then take this authorization policy and put it into our IKE v2 profile. And that's how those pieces link together. Now, regarding the IKE v2 authorization policy, we have a couple of options. Number one, we could create a brand new one, or we could tweak or customize the default IKE v2 authorization policy. And let's go with that option. Crypto IKE v2 authorization policy default, and we'll say route set, the keyword access-list, and then we'll point to that access control list that contains the 10.2.2 and the 10.22.22 networks. Now, in our case, in this lab environment, I know that there's nothing else on R2 that is using the default authorization policy. And as a result, I know that there's nothing else that's going to break as a result. So in a production environment, be very aware of what components are using the default policies and profiles. And if you're not sure on a device whether or not something is using the default policy, my strong recommendation would be don't mess with it until you become sure. Next, let's take a peek into a show crypto IKE v2 authorization policy just to confirm what is in it. And this looks great. Our route set for ACL route-ACL implies that the 10.2.2 network and the 10.22.22 network are going to be advertised from this FlexVPN client up to the FlexVPN server. And it's also willing to accept any routes that are advertised to this router. And if we wanted to, we could also put controls on the networks that are acceptable or receivable by this router. Now, our next step is to take this authorization policy, the one called default, and we're going to tuck it into our existing IKE v2 profile that we created previously and are currently using on R2. So to do that, we'll go into crypto IKE v2 profile configuration mode for IKE v2-profile, and we're going to use the syntax AAA authorization group cert list author-list default. Now, that is a mouthful, I know. So let's break down that command. AAA authorization group implies that we're doing group authorization compared to what? Well, compared to user authentication. We're going to use digital certificates. The cert means that if we've already authenticated a peer using our digital certificates and RSA signatures, effectively from the local router's perspective, that also means that that person is now authorized. That's what this command refers to. The list, author-list, is the AAA method list that we created earlier, which basically refers to the local router itself, meaning the router's not going to go ask a AAA server group, and R2 is figuring out the authorization question by asking, have I authenticated this peer using digital certs? And if the answer is yes, then the router locally says that's 2 thumbs way, way up. This customer or this peer is also authorized. And the last piece is this word default. This is the name of the IKE v2 authorization policy, specifically this one right here, that is going to be used. And as a result, because we have the route set ACL route-ACL, that means that R2 is going to advertise to the FlexVPN server the networks of 10.22.22.0/24 and 10.2.2.0/24, because those are the 2 routes that are inside that access list called route-ACL. Next, we get to configure the client FlexVPN portion. The syntax for that is crypto IKE v2 client FlexVPN, and then the name that we want to call this client configuration. We could call it our client or your client or Bubba. It doesn't really matter too much. And that puts us into client configuration mode for FlexVPN. One of the items we absolutely want to identify is the peer. Who is the peer we're going to connect to? And we have priorities. For example, peer number 1 would be our first preference. So if we had 2 or 3 different head ends that we could connect to, we'd put in peer 1, 2, and 3 with their respective IP addresses. And if the first one doesn't respond, we'll go ahead and try with the second one and the third one. As long as we have more in the list, we'll try more. If we do a question mark and take a look at our other options here for the FlexVPN client, the connect option lets us identify how we want to connect. Do we want it to be a manual process, or do we want it to be automagic, meaning we put all the parameters in and the FlexVPN client will automatically just build the tunnel for us up to the head end. We're going to tell the FlexVPN client what our inside interface is. For example, if we had gig 2/0 on the inside of R2 that was connected to the local 10.2.2 subnet, we would say client inside and that interface. In our case, on router 2, I'm using loopback 1 that has the IP address of 10.2.2.2/24 to represent that inside our local network. So in my client configuration, I'm going to tell it that's my inside interface is loopback 1. We're also going to tell this client which tunnel interface it's going to use to build the tunnel to get up to the FlexVPN server. So in this example, we said, okay, we want you to use tunnel 0. We had previously been using that as a static tunnel interface. And once we gave it that last piece of information, because connect mode was set to auto, it automatically reached out and built that IKE v2 tunnel and the subsequent security associations for IPsec between itself, R2, and R1, which is the FlexVPN server. So we'll get out of configuration mode. Now, before we rush out and start configuring this on R3 and R4, the other 2 spokes, let's do a few verification commands just to make sure that everything's working like it should. From here, let's do a show crypto engine connections active. I love that one because it shows us the big picture of all the tunnels that are in place, the IKE v2 hopefully, and the IPsec essays. And that looks great. And we could verify the source and destination of the tunnels with a show crypto IKE v2 essay. And that shows it's between us, 25002, and the remote, which is R1 at 15001, which looks great. And if we make a road trip up to R1, and on R1, if we do a show IP route 10000 to show us all the routes that begin with a 10, you'll notice we have this beautiful 10.22.22 network. And that's because the FlexVPN client R2 had that access list, which was referenced in the IKE v2 authorization policy, which was included inside the IKE v2 profile that was used for this tunnel. And that's why that network got pushed up to R1. And we'll also notice that 10.2.2 also appears in this list. And this route that was learned from the FlexVPN client has a better administrative distance, and that's why it's showing up instead of the OSPF learned route of 10.2.2. And the other funny thing is this route of 10.22.22, that network doesn't even exist at all. We just included that network, the 10.22.22, in an access list on the FlexVPN client, and that's why it's showing up here on the FlexVPN server, because it was part of the policy on R2. So if we tried to ping 10.22.22 something, because it doesn't really exist, that packet would be forwarded over to R2, and R2 would say, I don't know what this is. So let's do a quick fix on that. Let's go over to R2, and let's create interface loopback2. I just want to verify it doesn't exist first. So we'll do a show IP interface brief. Okay, no loopback interface 2 yet. We'll create one, and we'll give it the IP address of 10.22.22.22 with a 32-bit mask. Now, just to verify that this network is not being advertised inside of OSPF at all, we can do a show IP OSPF interface brief just to confirm that loopback number 2 is not inside OSPF, not participating. And now if we ping from R2 to 10.1.1, which is an internal network to R1, and we source it from 10.22.22.22 because R1 has learned about the route to 10.22.22 from us pushing it up to him. Because he has the route, R1 does, he can reply back to the 10.22.22.22. And just to verify that that really is going over the IPsec tunnels, we can do a show crypto engine connections active. I like that command because it's much more concise output regarding quantities rather than digging into the output of a show crypto IPsec SA, which also gives us the information, but a bunch more that we may or may not need at that moment. So that looks great. So because that works, let's go ahead and configure R3 and R4. We'll do it a little bit faster, but it'll be a great review of the commands. So on R3, we're going to enable AAA. We're also going to create a method list for network authorization. We'll call it author-list, and we'll specify that mode as local using the local router. We'll also create interface loopback 2 on this router. We'll give it the IP address of 10.33.33.33. Although it's not going to go into OSPF, we are going to advertise it via our authorization policy. So we'll create an access control list. We'll call this R3-route-ACL. We'll specify 2 networks, 10.33.33, that's the one we just made the loopback for, and 10.33, which is one of our existing loopbacks already. We'll tell this tunnel interface, which was previously pointing for tunnel destination up to R1, that we now want the tunnel destination to be determined dynamically. And because it no longer knows about 15.0.0.1, the tunnel has come down. Next, we're going to modify the default IKV2 authorization policy here on R3, and we're going to say we want to do route set the keyword access-list and the name of that access control list we just created that identifies the 10.33.33 and the 10.33 networks. The benefit is that we can now advertise the reachability of those 2 networks that are mentioned in the access list up to the FlexVPN server, so it'll have routes to those networks. Let's do a quick show command. We'll do a show crypto IKV2 authorization policy just to make sure that what we put in is exactly what's there. So we're not filtering on any routes that we're willing to accept. We're also including the contents of the access control list, R3-route-ACL, regarding what we're going to advertise up to the FlexVPN server when we build and establish our tunnel. Next, because we're using an IKV2 profile called IKV2-profile, let's go ahead and modify that profile by going into configuration for it and then specifying AAA, authorization, group, cert, list, refer to our method list we created earlier on this router that's using the local database, and then the name of the authorization policy, which is called default. Next, we're going to create our IKV2 client. And to do that, we'll type in crypto IKV2 client FlexVPN, the name of our client. We'll specify the peer. We'll tell it that we want to connect automatically. We want to tell it that our inside interface is loopback 1 and to connect using tunnel 0, and that should automatically go ahead and build the tunnel. And the OSPF has already come up, which means that the IKE version 2 negotiations, the authentication is done, the children SA, the security associations for the IPsec has happened, and we now have functioning tunnels, meaning the IKE v2 and the children tunnels working between R1 and R3. So our last step is R4, the final spoke, and on R4, let's go into configuration mode. We'll enable AAA new model, and we'll also create a method list for network authorization, just like we did on R1, 2, and 3. We'll also create loopback 2 while we're here. We'll give it the IP address of 10.44.44.44 with a 32-bit mask. That way, if we try to ping it, because we're going to have reachability to it from R1, there will actually be a layer 3 interface on R4 who has that IP address who can respond to it. Next, let's create an access control list called R4-route-ACL. And inside that access control list, we'll identify 2 networks. Just as an example, the 10.44.44 with a 24-bit mask and the 10.4.4 with a 24-bit mask. And we'll include that as part of our IKE v2 authorization policy so we can advertise that from our FlexVPN client up to the FlexVPN server. Next, you and I are going to destroy a perfectly good tunnel interface, tunnel 0, by telling it that we want the tunnel destination to be dynamic as opposed to 15.0.0.1, which is going to cause the current tunnel to come down between R4 and R1. We're going to modify the default IKE v2 authorization policy here to include setting the access list R4-route-ACL as the reachable networks that R4 is offering up to the FlexVPN server. Now, just to confirm, before we modify the profile, let's do a show crypto IKE v2 profile just to confirm what profiles we have on this device. So we have the IKE v2 profile called IKE v2-profile, the same as we did on R1 and R2 and R3. The authentication method that we're using is RSA signatures. The trust point is trusted CA. The lifetime is 86,400 seconds, which is the default. Dead peer detection, although it's integrated into IKE v2, it's not enabled by default. We can turn that on if we want to. We're not referencing a virtual template. And at the moment, AAA group authorization is set to none, and that's the part that we want to modify regarding this IKE v2 profile that we're using. So we're going to go into configuration mode for the IKE v2 profile named IKE v2-profile, and we're going to specify AAA authorization for group based on digital certificates. The list we're going to use is author-list, which refers to local on the router, and default refers to the authorization policy called default. Our last step is to configure the IKE v2 FlexVPN client. So we're going to call the client on R4 our-client as well. We'll specify the peer with a priority of 1 is 15001. The connection mode is auto. The client inside is going to be loopback interface number 1 that represents the 10.4.4 subnet. And the client connect should be through tunnel 0. That should bring up the tunnel. And now we should have an IKE version 2 and the child SA tunnels built between R1 and R4. Now on R4, if we do a show IP route for 10.0.0.0, you'll notice we have quite a few routes. We have the 10.44, which is local. That's because of our loopback interface. We have the 10.4.4, which is also another loopback interface. We have the OSPF learned routes of 10.1, 10.2, and 10.3. But here's the challenge. R4 is not seeing 10.22.22, and R4 is not seeing 10.33.33 because those routes are not being advertised in OSPF. So even though if we went over to R1, and on R1, if we did a show IP route for 10.0.0.0, it's very likely that R1 is going to know all those because R1 is the FlexVPN server. All of its spokes advertise those networks respectively, and that's why he knows about them. So what we could do, if we want full connectivity without using routing protocols for those remote networks, we could play the route set game on R1. We could say, hey, dear Mr. R1, advertise an 8-bit 10 network out to all your spokes. Or advertise a 172.16.00/16 network to all of your spokes. And then those would show up in the routing tables of those spokes. So in the case of R4, if we look back at that for a moment, if he needed to reach the 10.33.33 subnet, and he didn't have a route for it, but he did have a route for the 10.00/8 network, that would be the longest match. He would forward that packet up to the hub, and then the hub, with a more detailed route, would forward it to the correct spoke. So on R1, we can simply manipulate the IKE version 2 authorization policy and use our own route set commands there to advertise, for example, the 10 network. So on R1, in preparation for that, let's go into configuration mode, and let's create an access control list called hub-ACL. And I'm going to include in it the 10 network, so permit 10.0.0.0 with a wildcard mask with 24 bits on at the end. And let's also, just for grins, do one other network. Let's permit 172.16 with a 16-bit mask. So the last 2 octets would be all on for the wildcard mask. And let's push that down to all the spokes. Now, primarily in our demonstration, the 10 network is the one that we're after. And the 172.16 is simply an example of a second network that we could also advertise and push out to our spokes. So on the hub, let's modify our IKE v2 authorization policy. We are using the default policy. So the syntax is crypto, IKE v2, authorization policy default. And we'll simply say route, set, access-list, and the name of our access list. If you're using a numbered access list, it would be the number of your access list. For verification, let's do a show crypto IKE v2 authorization policy, just to verify that that access list really does show up in the authorization policy. So the name of our policy is default, and sure enough, right there is our hub ACL access control list with the route set. And as far as the IP address pool that we're handing out from our previous video, it's still set to flex pool. To shake things up a little bit, let's go ahead and tell R1 to give up on all his IPsec and IKE v2 sessions with a clear crypto session. That's going to tear everything down. But I'll tell you what, IKE version 2 is pretty resilient. Those clients are going to say, hey, I lost my connection. It's going to try to rebuild automatically because we have Connect Auto set up. So based on our OSPF neighbor messages, it looks like we have a fully connected network once again. And that new policy should be now pushed down to each of the spokes regarding the 10 network and the 172.16 network. So to verify that, let's make a road trip over to R4. And on our 4, let's go ahead and give us a little visual separation here. So previously, this was the 10 networks that it knew about. And now we'll do a show IP route for 10.0.0.0 once again. And it looks very similar, except we have this extra route right here, the 10 network that's reachable over its tunnel 0, which, as we know, goes up to the hub. So if we wanted to ping, for example, 10.22.22.22, and if we sourced it from 10.44.44.44, that would verify our connectivity up to that remote network up on R2. It would also verify that R2 has reachability back to the source address of 10.44.44.44 due to that 10 network that it got, or R2 learned from the hub. And with our ping of 50 pings, it looks like we have success. And let's also verify our path. I'm going to turn off domain lookup for a moment so it doesn't try to resolve every hop in the path. And we'll do a trace route to 10.22.22.22. We'll source it from 10.44.44.44. And we're going to see this traffic is going through the hub. The first hop is the hub, and then it goes to R2. And that's exactly the path that it took. And let's do one final little trick. Let's go to each of the routers. We'll go to R1, and we'll simply remove OSPF from the router. So router 1 is going to do no router OSPF1. That'll get rid of that. And just for good measure, to make sure it's not running anywhere, let's remove it from R2 with a no router OSPF process ID 1. And we'll also remove it from R3 with a no router OSPF1. And we'll remove it from R4 as well with a config T and a no router OSPF1. So now on R4, if we do a show IP route for the 10 network, we've got this 10 address, which was advertised to us from the hub, from the FlexVPN server. And if we tried our ping again, we're going to be using to reach the 10 networks that we don't know of directly, we're going to use that 10/8 network. It's going to go up to R1. And for the return path, R2 is going to use its 10 network that it learned from the hub, from the FlexVPN server, to reply back to those packets. And so, without a dynamic routing protocol even running, we can go ahead and have full connectivity by using the FlexVPN and control the advertising of routes through the IKE v2 authorization policy. So if we were on a new network where we hadn't configured it and they wondered, is this working properly? What are some commands that we would use to help verify the behavior of the FlexVPN? Well, one, of course, is show crypto IKE v2 SA. If they don't have any IKE v2 security associations, they might have some ISAKMP ones. We do a show crypto ISAKMP SA. That would be for the IKE version 1. However, if they're doing IKE version 2, they should have at least one functional working IKE v2 tunnel. And this is the command that would verify that. If we want to see the children SAs, the IPsec SAs that have been created by the IKE v2 tunnel, we do a show crypto engine connections active. And that shows that we do have 2 unidirectional IPsec security associations. One for traffic going from us to R1, and the other for traffic going from R1 over to us. If we want to see the nitty-gritty details regarding those IPsec security associations, the command is show crypto IPsec SA. So here it's showing packets encapsulated and packets encrypted. And because we're using GCM, we don't have to use HMAC, but we're still getting the benefits of a digest for data integrity and authenticity for each packet. And for traffic coming in, we have 1065 de-encapsulations, 1065 decryptions, and we're able to verify the data integrity of those same amount. Now, the number in this lab environment is the same in and out because I'm doing pings all day long with one ping request, one ping reply. With normal traffic, those 2 numbers do not have to be equal. For example, a secure copy or FTP is going to have a lot more traffic going one way than the acknowledgments going the other way. So although they do not need to be the same number for encryption and decryption, there should not be a really high number on the encryption, for example, and then a 0 for the decryption. That would indicate that we're sending encrypted traffic all day long, but for whatever reason, we're not correctly receiving and decrypting traffic. And there's one additional command that's specific to FlexVPN Client, which we just configured R2, R3, and R4 to be, and that is the command show crypto IKE v2 client FlexVPN. That's just so we don't get it mixed up with the easy VPN client that Cisco used to support. And this is showing us our client profile name. We called ours our client. We also could have tacked the name our client to the end of this command. And that way, if you had multiple client configurations, you could see just the output of the one you're looking for. The current state is active, which is a good sign. The current peer is 15.0.0.1. So if we had 5 or 6 peers and we weren't sure, okay, which peer did we connect to? The output of this command will confirm that for us. We're using tunnel 0 interface. The source of that tunnel is E00. and the assigned IP address that we've been given by the FlexVPN server was 172.16.0.104. Whenever possible, I absolutely want you to practice what we've done together in these videos. There's no better way to help reinforce the concepts than to practice with it with hands-on. I've also included in the Nugget Lab files this document called FlexVPN Client and Pushing Routes Full Config Included.rtf. And what that has, it has all the commands that we issued today. In addition, it has the full final running config after the configuration was all done of the hub R1 and the 3 spokes R2, R3, and R4. And my intention in sharing this document with you is to give you a reference point and a foundation that you can refer to with all the pieces and parts in a working configuration to help accelerate your studies while you're practicing and mastering FlexVPN. So again, I've had a great time. Thanks for joining me for this video. I hope this has been informative for you, and I'd like to thank you for viewing.